Kalash, don't record your sound.
Well, it's recording, but
It's very weak. Yes, but it
okay.
sounds very weak. Can you
Okay,
share it?
we derive quasi-linear diffusion in two different ways. First, we use the distribution function with F1, and then we looked at it from the point of view of particles undergoing diffusion in energy space, or it could be velocity space. You could do it just with the force here instead of v dot the force. And we noted that the variance in the energy diffusion is a double integral, but one integral separates out, so it ends up just being proportional to time. And when the variance is proportional to time,
It's variance or mean value?
the
What is it?
variance, it's the square of,
Ah,
that's called the variance, right?
no, I don't think so.
Mean squared.
Mean square. Variance is
root mean
something
square.
else. It's
No, mean square. Yeah, it's not root. So mean square.
Mean squared is also called variance, right?
Yes.
ah delta E. Right. Sorry.
So one integral ends up being proportional to time, and the other integral ends up being proportional to the correlation time of the phase.
Mhm.
But and then the other concept here, when you have gyration, is simply that the e to the I dot k dot r has a component rg sine theta plus k parallel, let's say z. And then you can expand this z is really is just a dummy variable here, but it should be krg in our particular case. So we then have this exponent is one. It's the product of two dimensionless numbers, and you can factor it as being the sum of two functions of the two separate factors in the exponent separately. And but now I want to do something that does not really connected to whether you have gyration or not. It's valid both for electrostatic waves and for cyclotron cyclotron resonance with electromagnetic waves.
Okay.
Which and remember, to have resonance you need v dot e, and for an electrostatic wave it's just the longitudinal motion that's going to be important. But for an electromagnetic wave where e is perpendicular to k,
Yeah, just what we did a couple.
then it's the gyrational motion.
Yeah.
That resonates. So the issue here is taking the average of two phases at two different times. this really defines the correlation time. When the time over which this goes to zero is called the correlation time. Now, how do we do this integral? Well, we assume that phi itself, which is the phase of the wave, obeys diffusion. No, this is not what I want to say. We just assume that
the phase difference in
phase difference, because it's both phases are Gaussian, and when you sum of two Gaussians is also a Gaussian. Sorry, the
product.
The distribution of twos, of the difference between two Gaussianly distributed variables is also a Gaussian distribution, because the distribution of x minus y squared is equal to the distribution of x squared how do you prove that the distribution of the difference between two Gaussians is also a Gaussian? You believe that, right?
You mean
if x has a Gaussian distribution and y has a Gaussian distribution, then x minus y has a Gaussian distribution.
The probability of their
x
independent
minus
variables
y into exponent, you mean? What do you mean? X minus y.
Oh yeah.
It's because
you can use
probability
the derivative. You can call it a new variable. Yeah. And you can use the
no, I think it's because we have
derivatives.
two independent variables, and so the probability should be multiplied of getting x minus y.
That's right. Alright, even instead of talking about it, let's just do it.
So
the point is we want to take we want this integrand to be viewed as a Fourier component of this, and the ensemble average is a Fourier component of this. Probability of distribution of this quantity is given by okay, here I assumed it was a Gaussian that had a separation that was proportional to d times the time difference, where d here is the diffusion of the phases in not phase space but angle space. But this now has me intrigued. How do you prove that the distribution function of I assigned it for homework, but it doesn't really have to do with this course. But I think I'll just state it. The distribution of the difference between two variables, each of which is distributed in a Gaussian manner, is also a Gaussian.
I think you can do it by calling the difference as a new variable.
It is a new variable.
Like the distribution
The
down.
probability of
L.
the probability of x minus y is equal to
Probability of x times x minus y and plus y. These are two independent variables, px
Px plus py
No,
plus
times.
the covariance term, no?
No, it's
Yeah,
time
but
because
they're
there's
independent, so covariance
Oh no,
goes
it's the
to
variant.
zero.
No, I'm talking about the
You
variant.
no,
The variant. I'm
okay,
making a
it's
mistake.
it's
Yeah,
the integral of px
yeah.
py but integrated over dx plus y such that x minus y is constant.
Yeah. Or
Um,
you can introduce delta function. And now you can write simply x minus y as some variable z.
this
Right.
is equal to e to the minus x squared over let's say dxxt minus y squared over dyyt.
I think it's simpler to write instead of y x minus z and then integrate over z. I mean, if you write x minus y as z, let's say.
Yeah, x minus y is z.
Yeah. And then z is a fixed number. You
No,
integrate.
z is a fixed number,
Yeah.
and x minus y is a fixed number.
And then you write
So here I'm writing dx
dx
plus y.
if you do that way, then you have to integrate this in one variable,
What?
dx. If you write that way, z is a fixed number, and then you write
Just a second. I can write this as Go ahead. Sorry, what?
if you write x minus y as z here,
Yeah.
then here you write e to the minus x squared, and here you write z minus y minus z squared dx.
Okay. E to the minus x squared minus z what?
So y
Z
is,
minus y?
yeah, squared. So z minus x squared. Yeah.
No, it's z z minus x squared over dyyt.
This should be integrated over x.
Integrated over x.
Yeah. So I think z squared.
Well, I'm
out.
not sure because it should be really integrated over x plus y.
But y is dependent variable. You
No,
replace.
z is held fixed,
Yes.
and therefore
Y was fixed.
no, if x changes and y doesn't.
Gives you
Alright.
what is y?
No, if you fix
Y is
z,
x minus z.
Alright, so let's do it. E to the minus x squared.
Y is z.
minus x.
Y is x minus z.
Yeah, but it's square, so it doesn't matter.
This is gonna give me. I don't understand what this
dx
gets me.
plus y.
No, then you have only
I don't understand what this gets me.
you are integrating. I think you y z squared plus x squared. That's one part is simply integral Gaussian, so that is a factor, some factor. One is z squared. But it's simply a number.
No, I think what you have to do is do this. you say z plus is equal to x
I think it's minus
plus
z squared.
y, z minus equals x minus y.
You can do that by
X,
z squared
x,
comes out there and you get a number.
what?
In the way you written previously.
And x squared plus y squared is equal to z plus
But in the previous expression which you just erased,
yeah.
if z squared just maybe I can do here and you can do there.
I guess this clean piece of paper. Yeah, plus z minus squared. Yeah, okay. I think this works. I just write that is equal to e z plus squared
How did you write it?
Alright, I seem to have proved that if dxx happens to equal dyyy, which in this case happens to be true. So let's just... It just fucking goddamn happened.
Maybe it's on the. Oh, maybe
Yeah.
you should press on the NE over there to the left.
Yeah.
Maybe it will be there. You see to the left, you have an enter.
Yeah.
Oh.
Alright, in the special case where dxx is equal to dyyy, first of all I want to make this over the square root of 2. This is certainly true.
No, then you should have it in brackets. Minus z plus z minus z minus square.
What?
It should be in brackets. I mean, the
What
minus.
should be in
Oh,
brackets?
I'm sorry. The minus here. You should put a bracket here because z plus square plus z minus square gives you x.
That's, yeah. And then I just integrate over z plus with
And it's just a number.
and
Pi
so
or
it's
something.
proportional to e z minus squared.
Yeah.
But that's in the case of the.
I think what I would do when the d's are not equal is normalize the y appropriately. Just put some coefficient in front of the y that cancels out the
Yes.
so if I compute this quantity now, it's this distribution function times this number. And You believe that that's equal to this? If you insert e to the minus phi prime minus phi double prime
No, it's without the minus.
square, what?
It's without the minus.
Where?
I'm reading it from here and I don't see minus here.
No, there should be a minus.
Why?
There's a minus here, right?
It's the same as this one, no? I mean, this is the same as this one.
Maybe
That's right. Phi prime is phi k of t prime. And
So there is no minus in there. I mean, maybe there is.
what? There's no minus in where?
Sorry, in here. Maybe there should be.
Yeah. Here there should be a minus. Nope. There's no fucking way to write this. Right?
Maybe your hand
Without
is
touching it.
Maybe.
Yeah, but I can't write without touching it. And not only that, but if you keep your hand far away, then the angle is too low.
No, I think it's not in pen mode. Probably. No, you probably keep it there the whole time.
Look, I drew it. I did it. There's a minus sign right there.
Yeah. Okay.
All right. Gamma is just this.
But you need to
so-
divide
so-
by the.
So the way you do this is that you complete the square.
Oh, wait, but you need to divide by the.
Goddamn fucking son of a bitch. Goddamn fucking son of a bitch. Goddamn fucking son of a bitch. Okay. The idea is if I complete the square,
You still need to divide by the.
this is over D. Okay, what do I need? I need to add one more thing to complete the square. In other words, I do plus plus what shall we call it? Zeta minus zeta. And this should be a perfect square, so that when I integrate over no, first of all, let's get something straight. This is an integral over phi. If you figure out what this zeta is, you'll find that this integral is equal to this. in other words, when this quantity is large, when t prime minus t double prime is much greater than 1 over d, where 1 over d is the correlation time. Gamma is the decorrelation rate, and therefore 1 over d is the decorrelation time. And when the time separation is much bigger than that, then you can just see that this factor is going to enter into zeta. And when you integrate okay, what does rho have to be? What does zeta have to be? Zeta has to equal d phi phi. I'm just going to write delta t. And then I think I want to make this a minus. Okay? You believe that this is equal to this squared?
Yeah.
Okay, so therefore I want to make this I want to make this I guess. No. No, zeta is just minus dw. Because I added zeta, which was the square. I added rho, which was the square of what I needed to complete the square. This here is the square root of zeta. This term is the square root of zeta. No, with the a. Because zeta has a minus sign. And this is just a constant, so this I take outside of the integral, and then this being a perfect square is a Gaussian distribution function in the quantity delta phi, so that's just a constant because it has to average out to unity, and therefore this factor e to the minus zeta is this. And I seem to be missing I'm probably missing a minus sign somewhere, but
what about the delta t? Zeta was...
You're gonna have to ask a better defined question. Where should the delta t be that it isn't?
I'm sorry. In the gamma, because you said that zeta was d delta t.
Yeah, but this is delta t.
I thought it was a function.
Because this was a minus sign here, so this actually has to be a plus. So I added the plus in here, but because there was a minus outside, I also add a plus here, and since zeta is minus this gamma delta t, then it's the exponent minus gamma delta t. Okay, so now if I do this integral, all this this is the integral over delta t. Now here the integral really is over delta t. And this here does not contain, this term here does not contain the phases. So this is just, we're just Fourier transforming some function of delta t. See? This part is a constant factor, the part that doesn't depend on delta t. This part depends on the delta t, but it's a Fourier transform of this, which is a function of t. What function of t is it? Well, it's this function of delta t. And by the way, it turns out this is an absolute value. Oh, I wrote absolute value here. Note, this is absolute value. If I switch t prime and t double prime, it doesn't change because the correlation goes back in time as well. And that's because there should have been an absolute value here as well. Okay. So this is just a Fourier transform of this function, and the Fourier transform of this function is well known. It's equal to this. So now, look what we have here. We have something that's approximately a delta function. As gamma goes to 0, as gamma goes to 0, this is a delta function in this quantity here. It's a Lorentzian, but as the width of the Lorentzian goes to 0, it becomes a delta function. So it's really a delta function of what's inside these parentheses. And that's, if you take omega equals 0, that's the same resonance condition we had before. But note that we get the sign. We note that the pole is automatically lifted off the v-axis by the presence of a finite gamma, which means that the ability of the phases to get random and forget their initial correlation is what determines where the pole is. And you can see it's the same place it was before. Actually, this still has two poles, so you still have to figure out which one to take. But the point is, does it
Why
plus and minus I gamma? What's in this parentheses?
Everything. Oh, yeah.
So come to think, you still have to decide which direction time is going in. But you see, this is just particle diffusion in energy space, and all I've really shown is that the diffusion coefficient in energy space depends on the spectrum of the waves, the E squared of the waves convoluted by this Lorentzian. So the final diffusion coefficient.
I just want to understand what is written here. If gamma is about k dot p, it's not zero.
That's right. It's not zero. This is
not supposed to be zero for it to be a delta function, as you said.
You see. If it's zero, it's exactly a delta function. If it's non-zero, but not too large. Now here gamma is of order this term, so it's a gamma squared. The half width of this kernel is just when omega minus kb is of order kv. In other words, it looks something like this. If the resonance is here, it's as wide as the actual resonance, but it's not.
No, it's approximately.
I'm just saying that if really I'm cheating a little bit because it's a pretty fat delta function, but I'm just saying that if you can approximate as a delta function, then you can go back to this integral over k prime and pick out over k and pick out the values of k where the delta function picks out, and it's an integral over a delta function, and then you're basically done because you just you're picking here this u squared v squared was actually e squared. It's the wave spectrum. You could think of u squared as being the energy in the wave, and these arguments being the value of k. Now, for homework, just derive dVV for electrostatic waves. Which is what I was going to do if my notes had been put here. But I think it's better if you do it. You just go through all these. It's much easier than what I did here because there are no Bessel functions. It's just you just start with, you use electric fields. There's no U cross B. You express things. You express the wave spectrum not in terms of u squared, the velocity, but in terms of the electric field squared. You just go here. E is energy, but when you write E, you'll be to mean the electric field, and you'll get something proportional to with the delta function will be a gap. It'll actually be this. I want you to do it go through the whole thing again.
Here is the electric field, it's not the energy.
That's right. Here it's the electric field. No.
It's square. The square is the...
No. Here, script E is the electric field. This here is the change in energy. Because the change in energy is V dot the force, and the force is Q dot E. This here is the electric field. Okay. So that's it for quasi-linear theory. And I guess next time we can start hydrodynamics. How many more weeks do we have in the course?
3.
Only 3?
Wait.
4.
No, we have one more in December.
No, 4.
4.
3 full weeks in January. All right. So that should be okay. We should get finished. What's the colloquium?